Hi, here are the solutions for your multiple choice limit questions from Chapter 4. That's my name, Chris. So let's see. I'm going to do what I asked you not to do, which is to do the work right on here. I have some extra paper here in case I need it, but see how we do here. So what's the limit as x approaches 0 of this expression here? Well, let's plug in 0 first and see what we get. So e to the 0, which is 1 minus 1, that's 0. Tangent of 0 is 0, so it is a 0 over 0, so I can use L'Hopital's rule. So let's see, the derivative of that, derivative of e to the 2x is e to the 2x times 2. Derivative of the 1 is 0. The derivative of tangent is secant squared. And when I plug the 0 in now, I get e to the 0, that's 2 on the top, which means no more L'Hopital, right? And the secant of 0 is 0. Is 1, sorry, that's cosine of 0 upside down. Squared is 1, so that's 2. Here, let's see. If we plug in a 0 here and we understand that this h is like on the bottom, that this is like a 0 over 0. So I'm going to rewrite this. So h approaches 0. The natural log, I don't know why it's written like that. I would rather have like 2 over 2 and h over 2. We'll call that 1 plus h over 2, right? That's the same. I like that a little bit better. Or you could even write it as 1/2 h if you wanted to. And then that 1 over h, I'm going to put that on the bottom. And I'm going to check, plug 0 in here. Natural log of 1 is 0 over 0, yep. So I'm going to use L'Hopital's rule, which says here the derivative of natural log of whatever is 1 over whatever. Sorry, I forgot to write this down. 1 over whatever times the derivative of what's inside, which is 1/2, right? It's like 1/2 h right there.
Amanda Merrill, please dial extension 350.
Over derivative of h is just 1. And I think I can plug in my 0 now. If I plug in 0 here, I get 1 over 1 times 1/2, which is 1/2. And here's an old like pre-calculus kind of limit. You might have just looked at this and said, oh look, n is approaching infinity, so it's the highest power top and bottom that matters, so it'd be like 4n squared over n squared, which is 4. And that's right. But remember, if you plug that in, it's an infinity over infinity, so you can actually use L'Hopital here if you don't recognize that or you remember that. Since it's going to infinity top and bottom, you could say, okay, I could take the derivative, that's 8n over 2n plus 10,000. That's still infinity over infinity, so I can use L'Hopital again. And that's 8 over 2. Well, that's just 4, right? So L'Hopital works on those too. And you can see how the derivatives, how that's happening. All of the lower powers are eventually going to get wiped out until you just have the higher powers left. Here, if I plug 0 in here, that's 0 times cosecant is 1 over sine, so that's 1 over 0, or that's like infinity, right? So I need to do some work on that, and the easier way to flip it over, which is going to work for you, is to say, well, cosecant is the same as sine on the bottom. And then maybe you recognize from Chapter 2, this is that sine x over x upside down. That limit was 1. And of course it's still 1 upside down. But in case you didn't, then you say, okay, I'm going to use L'Hopital now. So as x approaches 0, derivative of that is 1, derivative of that is cosine x, plug in the 0, and now I get 1. Let's see. Number 5. If the limit is like a concept kind of limit question, good thing for us to be thinking about now. If the limit is x approaches a, if f of x equals L, in other words, so if this limit exists, which of the following must be true? Does the slope at that point have to exist? Well, gee, I don't think so, because if we had a function, I'm going to draw a little counterexample for each one. Here's like an absolute value kind of function, and there's the point A. So as x approaches A, the limit of this function certainly exists, right? It's coming into that point, no problems, right? Because this is just about the function. But the slope doesn't exist there, so that's not true. Does f of x have to be continuous at x equals A? I don't think it does, because I think we could have a situation where one of these kind of things. So here it's coming into the right place here, so the limit would exist. But when you actually get there, it's in the point's like in the wrong place. So I think it does not have to be continuous. Remember, this limit exists, right? It doesn't matter what happens when you get there. What matters is what happens as you get closer and closer. Does f of x have to be defined at x equals A? No, it could be like this. It could be like that one, just without a point at all, right? That limit would still exist even if there's no point at all. So it doesn't have to be true. Does f of A have to be equal to L? No, I think you can see from this example here, the actual thing, it might be not in the right place. So none of the above. None of those things have to be true. I haven't thought about that kind of stuff in a while, but good question to slip in here while we're talking about limits. Oh, here's another one like that, kind of concept-y question. So if f is a function such that the limit as x approaches 2 of f of x minus f of 2 over x minus 2 is 0, well, that means this should remind you of slope. This is like that second definition of the slope of a function at a point. So this, in other words, that says f prime of 2 is 0. That's what that says. Right? This says the slope as these things get closer and closer together is 0. So is the limit of f of x as x approaches 2? No, it does exist. It's 0. Wait, hold on. Let me read that again. The limit of f of x as x approaches 2 does not exist. No, that's silly. I mean, what does that even say? I mean, the f of 2 exists, right? So do we know about the limit as x approaches? I think if we can talk about this limit, then we've got to be able to approach on both sides for this to exist. So I think that is silly. F is not defined at x equals 2. I think it is. I mean, there it is, right there, right? F of 2. It's right here. So f has to be defined at 2 to be able to make that claim. The derivative of f at x equals 2 is 0. Yeah, that's exactly what this says. This is the definition of the derivative. The derivative of f at x equals 2 is 0. That's what this means. Go through the last two just for fun. F is continuous at x equals 0. Ooh. Interesting. I want that to be true too. F is continuous at x. Oh, at x equals 0. No, sorry. This is about the point at x equals 2. Sorry, I got thrown off. If this at x equals 2, that would also have to be true, right? Because being differentiable at a point is a stronger condition than being continuous. But this is talking about at x approaches 2, so I don't know what's going on at 0. Who knows? So that doesn't have to be true. Does f of 2 have to be 0? Nope, it sure doesn't. The slope is 0, and f of 2 does not have to be 0. Alrighty. This also looks like the definition of the of slope at a point. The only thing that's missing, well, it's kind of x minus pi. Maybe it's a little different because this is all inside there. So we might be able to try to reason through that. But I'm going to go ahead and just use L'Hopital here. Make sure that we can. If I plug pi over 4 in here, sine of 0, which is 0 over 0. Yep. So take the derivative of the top, which is cosine of x minus pi over 4, times the derivative of what's inside is just 1, right? That's just a number. Over the derivative of x is 1. That's just a number, so the derivative is 0. Now I plug the pi over 4 in here, and that gives me cosine of 0, which is 1. Here, So this one has x's in here and x's up here. That means I'm going to have to do that little logarithmic trick. So I'm going to say the natural log of the limit I'm interested in is equal to the limit as x approaches infinity of the natural log of 1 plus 5e to the x. And then the 1 over x here, since I took the natural log, I can bring that to the outside, 1 over x. Instead of writing 1 over x, I'll put the x on the bottom. Okay? And pause there and think about what happened there. Make sure you're okay with all that. Now, let's make sure it's a L'Hopital form. Natural log of infinity, that's infinity over infinity. Okay, so I can use L'Hopital. So I do the limit as x approaches infinity. The derivative of the top is 1 over 1 plus 5e to the x times the derivative of what's inside, which is 5e to the x. I'm going to go ahead and put that up here on top, over the derivative of the bottom, which is just 1. Now, you can do L'Hopital again if you want, right? It's still infinity over infinity, and you'll get the limit as x approaches infinity, 5e to the x over 5e to the x. But I think it's pretty clear at this point or at this point that the limit is 1, right? This is like, it's like the same highest power thing. 5e to the x is blowing up, and this is exactly the same thing. The plus 1 as you go off to infinity just doesn't matter, right? And if you do L'Hopital one more time, you can see it actually disappears. So this is the limit as x approaches infinity. You might be asking yourself, but this is still infinity over infinity. Yeah, but it's exactly the same thing over itself. That's 1. No matter how big x gets, this is always equal to 1, right? This is a tie going off to infinity. So that means that the natural log of the limit that I'm interested in is 1, which means that my limit is e to the 1, or just e. All right, let's see what number 9 says here. If f prime of x, if the derivative of the f function is cosine, and the derivative of the g function is 1 for all x, f of 0 and g of 0 are both 0, then the limit as x approaches 0 of this. Well, if we plug 0 in here, I get 0 over 0, right? Which means I can use L'Hopital's rule. Which says I can use the derivatives instead, right? And when I plug 0 in here, I think I get, they told me what the derivatives are. It's cosine x over 1. So I can plug 0 in here, and I get 1 over 1. 1. So that's just sort of L'Hopital's rule in a more generalized, abstracted way, I suppose. Best way to do this problem, number 10, is to recognize this is the definition of the derivative. Derivative of what? Derivative of, that's where the f of x is, right? It's f of x plus h. It's the derivative of tangent of 3x. And the derivative of tangent 3x is secant squared of 3x times the derivative of what's inside, which is b. Now, if you want to, you can use L'Hopital's rule here, but you need to understand something. This is the limit as h approaches 0. That means that in this expression, h is the variable and x is just, you need to treat just like a number. It's not moving, right? H is the thing that's moving here, which means that x is to be treated just like a constant. Okay? And when you do that, you'll see that the derivative of the bottom here is just going to be 1, because that's the variable here. The derivative of this is 0, because x is not the variable. And you end up just taking the derivative of this, which is secant squared of 3 times x plus h times the derivative of what's inside, which is 3, and as h goes to 0, that just turns into this. So you can use L'Hopital, but you just end up taking, of course you get the same answer. So I think better to recognize it as the definition of the derivative. Number 11, if the limit as x approaches 3 of f of x equals 7, then what must be true? So that means I've got a function as x approaches 3, the y values approach 7. Does it have to be continuous at 3? No, it could be this kind of thing again, right? The point 37 could be where the hole is. So the limit would be, it's approaching that point, but when you get there, oops, something happens. But remember, limits are about what happens as you get closer and closer, not what actually happens when you get there. If that seems troubling, think about all the 0 over 0 stuff that we're doing. In all those problems, when you actually get there to that x value or that h value, whatever, it's 0 over 0. So it doesn't exist. I mean, it's non-existent. It's an indeterminate form there. Certainly there isn't any point if you tried to graph these things. So, so we need to understand we're interested in what happens as you get closer and closer, not about when you get there. Does f have to be differentiable at 3? Well, certainly it wouldn't be differentiable here at the same point, and also it could be like an absolute value situation. It could be getting in closer and closer to the point 37, but not be differentiable there. Does f of 3 have to be equal to 7? No, that's covered by this example, so none of those have to be true. Here, definition of the derivative again. This is very much like number 10. So this is the definition of the derivative of the sine function, and the derivative of the sine function is cosine. Right. Again, you can use L'Hopital. X is a constant, so that derivative of that would be 0, and you'll get the same thing. Number 13. This is just like the x to the 100 problem that we saw the other day. If you keep taking derivatives of this, and you keep k comes out, and then k minus 1, and then so on and so on, this just keeps being e to the x forever. But eventually, after many iterations of L'Hopital's rule, k iterations of it, you'll get down to this. Limit as x approaches infinity of k factorial, because k has come out, and then k minus 1, and then k minus 2. All those exponents kept coming out until finally all the x's disappeared, and you got this. Now you can't do L'Hopital on that, right? Because it's not 0 over 0 anymore. This is a number over infinity. Or it's not infinity over infinity anymore, I should have said. So this is a number, albeit a large one, possibly, depending on what k is. So this is a number over infinity. A number divided by infinity, no matter how big that number is 0. Again, two ways to do this. L'Hopital, or recognizing that this is the definition of the derivative of something. I'll use L'Hopital here first. I plug in 0. That gives me 8 times 1/2 to the 8th minus 8 times, so that's 0 over 0. So I can use L'Hopital. Limit as h approaches 0. Let's see, what's the derivative of this? It's using the power rule. That would be 64 times 1/2 plus h to the 7th times the derivative of what's inside is just 1 minus, this is just a number. The derivative of this is 0. It's just a number over 1, right? And then I can plug the 0 in here. That's 64 times 1/2 to the 7th, which is 64 over 128, which is 1/2. Or you can look at this and say, hey, this looks like the definition of the derivative of the, it's the derivative of the 8x to the 8th function, right? I'm interested in the derivative of it at x equals 1/2. Right, so what's the derivative of this? It's 64x to the 7th, and then when you plug plug 1/2 into that, of course, you can see the math is actually exactly the same. You get 1/2. So f prime of 1/2 is equal to 64 times 1/2 to the 7th, which is 1/2. If you're wondering to yourself, wow, would they expect me to do that without a calculator? Absolutely. 2 multiplied by itself several times is not difficult math for you to do without a calculator. So, sure, that's fair game. All right.